Hi everybody, I'm Steve. Sorry I'm getting started a minute late. I was told that I would have an introduction and then that person disappeared and I didn't want to make you all sit here, so I'm just going to do my own introduction. So pretend I didn't say any of that, and then we'll just do this. Hi everybody, I'm Steve. I'm, in other news for technical difficulties, I use free software almost exclusively on my computer, and I like to say free software, I love it, but it does not love me. So this screen is actually blank, and that screen has stuff on it, so I'll be turning to look at this every once in a while, because Linux plus projectors, I mean, it half works, so that's better than not working at all, right? I presented at a Linux meetup recently, and they did not take this joke with as good of humor as you all did. I immediately got questions about, like, what hardware are you using? What distro? That's weird. The Lenovo always has a good... Yeah, anyway. All right, so this talk is called Rust plus Node equals Heart. And I know that this conference is a little broader than a JavaScript conference, but really this talk is more like Rust plus insert other language here equals Heart. I've actually given a different version of this talk at a Ruby conference where I substituted in Ruby for this. So if you're not a Node person, super hardcore, please just substitute Node with programming language of your choice. Although Node, Python, and Java and Ruby tend to work best directly in this comparison. So yeah. Hi, I'm Steve. I historically have done a lot of Ruby work, and I'm actually like relatively new to server-side JavaScript. So I've been laughing that I only work in programming languages that start with RU. So I used to do Ruby, and now I do Rust. I'm not sure how many more we can come up with that start with RU, but whatever. I work for Mozilla on Rust full-time. I do all the documentation. So if you've tried to learn Rust and you did not understand something, I'm sorry, it's my fault. My primary thing is we call it the Rust programming language, or the book. It's about 250 pages currently of just introducing the language. It turns out that programming languages are big and there's lots of stuff to them. And so yeah, so I'm full-time dedicated just to documentation. I'm here to share with you a couple of things today. This talk is primarily about three things. The first one is this thing called systems programming in general. The second one is Rust, and then the third one is Rust and Node together. One other fun thing about this font that I have, let me actually zoom this. So that emoji on the end there is my favorite emoji. Its short name is called Sweat Smile. It's basically smiling with a little anime sweat on it. It's a little hard to see with the smaller font, but yeah. All right, let's zoom this out. Cool. So I want to talk first about this thing called systems programming. So this term has, like all terms, in computer science, a lot of them have very poor definitions. We're very, very bad at agreeing what words mean. Like, have you ever asked someone what object-oriented programming means? You get 5 different answers based on, 3 different developers will give you 5 different answers about what object-oriented programming means. And it's the same thing with systems programming as well. And this is sort of a problem for me because Rust has tended to historically advertise itself as a systems programming language. But the problem is that means people insert whatever they think systems means. Like all definitional arguments, I'm going to solve this by introducing a new definition of my own. And so when I say systems programming, this is what I mean by it, and sort of what we think about it in the Rust space. This was not my own idea. I blatantly am stealing this from Yehuda Katz, who you may know as a heavy Rails contributor back in the day, and most recently Ember.js. He's also on the Rails core team with me as well. And his definition of systems programming is my favorite. So that's systems programming is the kind of programming when it matters. And the problem with this definition is that it's making a reference to a thing it does not actually explain. So for example, in the Ruby world, we say Ruby is really slow, but it doesn't actually matter because your database is going to take up much more of the time than your actual web request. Or if you're writing in a language like Python, you might say it uses more memory than something lower level, but that doesn't matter because I'm actually looking for development speed time, and so I'm using this language for that reason. So programming and engineering in general is all about trade-offs and choosing the appropriate trade-off for whatever your task is. And so I like to think about systems programming as being when those it matters trade-offs actually do matter. So when you can't afford to use 300 megabytes of RAM for a Rails process, when you can't afford for your application to respond in a slower amount of time because a garbage collection pause caused your application to freeze, or when you need some sort of soft or hard real-time requirements, and so you can't handle arbitrary pauses at all. Or control in general. So if you're maybe working with some hardware, you need specifically to know the memory layout of the stuff that controls that hardware, and you can't just let your language decide the memory layout of your stuff. You need to define it specifically. So this is what I think of when I think of systems programming. It's like when you need to care about the details. And that doesn't mean that you have to care about every single detail all of the time, but you have to be able to care about the details that you want to care about. And so this is sort of where Rust has poised itself. It's sort of amongst the lowest level of the programming stack. So you can rewrite an operating system in Rust if you want to. You can write a memory allocator in Rust if you want to. One of the biggest names is using Rust in semi-production. They're not actually in production yet, but they're hoping to be soon, is Dropbox. So they're rewriting some of their stuff that controls how their files are stored on the hard drives in Rust. And so that's kind of the sort of broad spectrum of what I'm talking about here. And now, so the thing about talking about all that super low-level stuff is when I start talking about things like where your files are stored on the file system, or I need to care about the memory layout of my stuff, the reaction of a lot of people in the web space, where I've sort of been in the last couple of years, professionally speaking, is they're like, I don't want to have to care about all that stuff. And that is a super 100% valid thing to do. I myself cannot care about everything all of the time. It's just not possible, right? Because everything is a trade-off. So one of the other things about systems programming is I think that a lot of people who are in the web space, when they see things like control the way your memory is allocated or laid out in memory, they go, oh my God, that is super hard. I'm not very good at programming. I don't know how to do this. And so one of the major messages that I want to tell you is that it is not actually that hard, and you are in fact that smart, and I believe in you, and you totally can do this stuff. I actually know people who think that web programming is harder than writing an assembly code, because to them, assembly does exactly what it says on the box. There's only a couple of instructions. It's very simple and straightforward. Whereas to make a website, you have one programming language generate a markup language and a scripting language and a template like styling language, and then you bundle them up together and you ship them onto another computer on the other side of the world, and you expect that to all work. And so web programming is actually very complicated, and there's a lot of moving parts. And if you're a web developer, or if you work in these higher levels of the stack, you're actually doing really complicated stuff, and it's hard, and you should be proud of the work that you're doing. I'm not really interested in saying that certain kinds of programming are better or worse or harder or easier. I think that we as people are all very different and have different strengths and abilities, and so it might actually turn out that you think that writing file systems is easier than writing Ember, and that's totally legit. And so I think that one of the great strengths of Rust is that we are explicitly interested in helping you learn this kind of lower level programming language stuff if you are interested in it. So as an example of this, some of the code in this talk is actually based on, in my official documentation, I actually have an example of writing a library in Rust and then calling it from Ruby, Python, and JavaScript. There's actually a chapter in the official documentation just about the stack and the heap with regards to memory allocation and what that means. So we're very interested in helping you out. If you have not done this kind of programming before, and if you're interested in it, we will be happy to explain this stuff to you. And I also know that this is true because I myself underwent that relatively recently. So I learned C as my second programming language a very long time ago, and then basically when I found Ruby, I was like, cool, I don't need to worry about any of that stuff anymore. I'm never writing this ever again. So I went and did Ruby for a couple years, and I forgot all of that low-level systemsy programming stuff. And so when I first started working in Rust about 2.5, 3 years ago, it was Christmas 2012. Yeah, it's 3 years ago. I'm 2.5, I'm getting old. When I started working in that, I went into the IRC channel and I was asking people how does Hello World work? And they all helped and were friendly and were willing to explain it to me. And I was like, I don't understand this memory allocation stuff. Can you help me out? And they were like, absolutely. And so we've kept that sort of community spirit of being helpful, and no question is too quote unquote easy or simple or stupid. And so yeah, so this is sort of an explicit Rust community goal as well, which is really nice. All right, I have to zoom this slide out a little bit because it's got more stuff on it. Yeah. All right, right there. So enough talking about how sweet everyone that uses Rust is. Let's talk about the programming language itself. So Rust as a language is trying to accomplish 3 goals. The first one is safety, the second one is speed, and the third one is concurrency. And so there's many different ways of looking at programming languages and like aligning them up against each other for way too involved internet arguments about who is like better or worse. But one of the ways that you can sort of look at programming languages is this trade-off between speed and safety. So some programming languages, and I actually think speed and safety is only sort of half of it, so it's like speed and control versus safety and lack of control. So on one hand, you have programming languages like C and C++, and those programming languages give you a high degree of control over what you're doing, and therefore they have no safety whatsoever, right? Like programming in C is like driving without a seatbelt or like riding a motorcycle without a helmet. Like you can do it and it works most of the time, but it's very dangerous. And languages like Ruby and JavaScript to some degree and Python are sort of on the other end of the spectrum. And they don't give you very much control over how your code executes. They do to a certain degree, but not nearly to the degree that something like C or C++ does. But the advantage that you get is that they have a significant amount of safety. So for example, if you write some Ruby code that well, Ruby does technically compile or whatever, I don't get into those definitions. If you write some Ruby code and run it through the Ruby interpreter, it will not segmentation fault. Your app will not crash outright. And that's sort of a guarantee that's provided by the language. Whereas, if you write some bad C code, it will just crash on you with a terrible error message and not give you any help in figuring out what went wrong, right? So historically speaking, this has been this trade-off, and different languages are kind of in different places. I decided to randomly put Java here because it gives you a large amount of safety, but also does give you some degree of control. But really, you can argue forever about where languages are placed on this spectrum. But we in Rust sort of want to give you the speed of C and C++, but the safety of Ruby and Python. And as I said earlier, engineering is all about trade-offs. And so if someone tells you that this trade-off doesn't exist and you can have your cake and eat it too, they're probably lying to you, which means I just lied to you. So where is the trade-off in this in the Rust world? And basically, in Rust, the way that we provide this safety is through extensive compile time checking. So there's this phrase that people use to describe their early days of programming in Rust, and they call that fighting with the borrow checker. And the borrow checker is the name for the most unusual and unique aspect of Rust's compile time safety checks. And so at first, when you start programming in Rust, you will make mistakes. And unlike C or C++, where it will compile and then just crash on you, the Rust compiler will not actually compile your code. And it will say, hey, there's this problem here. You need to address it. Sorry, you don't actually get your program. And so I don't like to think of this as fighting. I like to think of it as having a friendly conversation. The compiler is there to help you. It's not trying to, positioning it as fighting means that the compiler is out to get you and it's mean. I don't really like that. I like to think about compiling languages that have really strong type systems, like Rust does, as being your friend who is convincing you that what you're doing is a stupid idea and stopping you from actually doing it before you hurt yourself. So I like to think about this as more of having a dialogue with the compiler where it informs you of your mistakes, because the good and bad thing about machines is they're not like humans, so they never sleep and they always do the exact same thing all the time, right? So they, in a certain sense, bugs are mistakes, but assuming that your code is reasonably bug-free, they don't make mistakes, they never forget, they're always vigilant against your programming errors. And you as a human, will make tons of mistakes. I know this is true now. One of the funny side effects is that when I go back into languages like Ruby and to some degree JavaScript, I'm so used to just typing crap into the computer and letting the compiler tell me what my problems are that I feel very, very nervous without that kind of help now that I'm sort of used to doing this heavy static typing. And so it's interesting when you switch between programming languages. When I was preparing an alternate version of this presentation, when I was preparing this presentation, actually, I was switching between Rust and C and C++ and JavaScript. And like when you try to switch between that many languages that quickly, I started like mixing the syntaxes up, and I was like defining a function according to the Rust syntax, but then writing the function in like JavaScript syntax, and like, you know, it gets complicated, but it's fun, and that's why we're here. Yeah, so that's sort of how Rust provides this speed and safety and like breaks the dichotomy. Is we have really strong checks at compile time, and that means that your code can be very efficient at runtime because you don't pay any runtime overhead for these safety features. They just compile down to the same code that your C and C++ code would compile to. We've just checked beforehand that you're not doing anything terribly dangerous. Let's look at a little bit of Rust code. One cool thing that you can do, let's see if the internet is still working. Yeah, typing. So play.rustlang.org is actually an online version of the Rust compiler, and it says that it's loading. Yeah, there we go. It took me a minute to even connect to the internet earlier, so. All right. Oh, there it goes. Awesome. Cool. So I'm gonna like tilt a little bit like this so I can do this. But let's see, does this actually work too? Yeah, there we go. Cool. So Rust, as a strongly statically typed language, has a little bit of sort of ceremony and syntax. To JavaScript programmers, it should feel a little bit familiar because it also uses lots of curly braces and semicolons. Although I know all JavaScript people don't use semicolons. I don't want to get into that whole argument. Talking about that, I use semicolons in my JavaScripts, but yeah, whatever. This is, I think I'm like legally obligated as a person to show you hello world, or you know, bad things will happen to me. So here's hello world in Rust. And the cool thing is then, so you can actually like, without installing the Rust compiler, you can type Rust into here and actually try it out, and so this will print hello world. So we sort of have this kind of thing. One sort of interesting aspect is that even though we have really strong typing, we also have really strong type inference. So for example, these double mustaches or lobster claws or whatever you want to call them, they're sort of like where the value gets placed. This is like a Pythonism. We decided not to use the C-style printf, scanf shenanigans and do the like, clamps. And so this is a strongly typed program, but I didn't actually write down the type of I. So Rust will automatically infer, if you don't have a good reason to, that your integers are a 32-bit integer value. So you don't have this sort of heavy burden of like writing out your types everywhere all the time. There's none of that like type name variable equals type name over again, other stuff that you might have in some statically typed languages. We do make you write types in function definitions, though. I'm gonna make this a little bit smaller. All right, so for example, this will actually fail to compile. I'm going to tell you that before it runs. It's not a live code mistake. It just doesn't actually work. So here I had to say foo is a function that takes one argument x. That argument x has the type f32, which is a 32-bit floating point number, and we print it out, with the hello world. And when I try to pass I in here, I get this compiler error mismatch types. Expected f32 found, I don't know. This underscore is like a little placeholder. So in this particular instance, that's because I'm passing an integer to a thing that has a floating point value. So Rust is complaining that I don't have these things. One cool thing that we've done is we actually have these error codes. And this to me feels like when we first implemented this feature, I remember back in my days of like learning Visual Basic as a kid, and I had this huge, thick manual that just had like descriptions of error codes. And so in some ways that was really awesome because now you have this E038. Let's see. Oh yeah, it's actually working. And so we actually have like extended compiler error messages that if you want an expanded version, we don't want to print this to your terminal. But this actually like explains this error occurs when the compiler was unable to infer the type of variable. It can happen in several cases. For example, x as an I32 is not a number. So we like put a lot of work into this compiler diagnostic stuff so that you can like get an extreme amount of help. this web page has all of them on it, and it is very long. And we're adding more stuff all the time. So that's also another cool thing that I really enjoy. We put a lot of work into trying to make these error messages understandable. So in that instance, I can change this to be 5.0, floating point number, and now Rust will compile and print that out. So this is kind of what I mean in the sense that, this seems like sort of a trivial thing for a person, but converting between number types that are wrong is a very good way to introduce subtle errors in your application. So Rust will sort of complain about it and make you do the right thing. And this does lead to a little teeny bit of like a difficulty of barrier to entry. Like I said, Rust sort of makes sure that you dot all your I's and cross all your T's before your code works. So at first you have to learn all of those things, which can take a little bit of effort. But after a relatively short period of time, you sort of internalize the rules. And a lot of people I've like helped on IRC, and I've watched them sort of be like, I'm having lots of problems. And then like the second week, they're like, I'm having less problems. And the third week, they're like, this finally clicked, and now I have no problems whatsoever. So that's also an interesting aspect of this sort of approach to correctness, because there's a little bit of upfront pain, but then it works out really well. Okay, so that's a little bit of an intro to some Rust code, so it's not totally alien. And so now I want to talk about Rust and Node, and I did not actually swip this out. I put Ruby in Node instead of Rust in Node because, like I said, switching between languages all the time is super hard. So Node is a really cool technology. I will admit that I have occasionally hated a little bit on Node on the past, but I think that Node is actually really great for a number of different reasons. And so I don't want to tell you, like, Rust is really cool, so stop writing in your favorite programming language, drop everything, and rewrite stuff in Rust. I don't actually think that that's, like, a good approach or a thing that you should do. I think that, you can like multiple programming languages. I don't know if you've told people that like to argue on the internet all the time, but you're, like, allowed to enjoy multiple things at once. You don't have to tie your entire identity into a single programming language. But instead of, like, making this about, like, Rust is cool and Node is drools or like whatever. It's about how both technologies are cool for different things, and so you should use them together because playing together is way better than fighting. So one really cool aspect of Rust is that Rust can make libraries that pretend like they're C libraries. And since C is sort of the Latin of programming languages, every programming language knows how to interface with C code because, we've buried ourselves under mountains and mountains of C code over the last, like, 40 or 50 years or whatever. And so Rust can sort of, like, masquerade as C, and what's neat about that is that means that you can put Rust inside of almost any other programming language because those programming languages know how to talk to C. And so in this case, I'm going to show you how to do this with Node. You can also do this with, as I said before, Ruby, JavaScript, Python, pretty much whatever, Haskell. It doesn't matter. And so you don't actually have to give up a language you already like. When you need this sort of lower level control, you can rewrite portions of this in a different language. So one example of this, I'll use Yehuda again. So his company Tilde makes this product called Skylight. It's a Rails performance monitoring application. Because I don't work for Skylight, I can tell you that my version of their pitch, this is not their official marketing, of course, my version of their pitch is it's like New Relic, but only for Rails, and therefore way better because they focus on just Rails. So they sort of like, you install their Ruby gem in your application, and then it monitors how slow or fast it is and why, and gives you feedback on what it is. So this Ruby gem that you install was originally written in Ruby, but since they're monitoring performance, Ruby's garbage collector would sometimes pause in the middle of taking a measurement of that performance, and you'd see weird spikes, and it's like, is that the app actually being slow, or is that the Ruby garbage collector decided to pause in the middle of taking a measurement? Like, I don't know. So you can like work around the garbage collector and do all this other crap, but basically it didn't work out very well. So they decided instead to rewrite this Ruby gem in Rust, and so that gives you all of this low-level control, as I've been mentioning. And so that enabled them to write this collector in a way that was much, much better. But what's cool is it's still a Ruby gem. So when you like gem install Skylight, you're secretly getting Rust code pretending to be Ruby code. And so you can do this with your own application. If you find there's a part of it that is too slow or taking too long, you can like get the MVP back in Silicon Valley. So I have to switch into your language. I live in New York these days. So you got to do your MVP to find product market fit. So you do that in a slow language first, and then you swap it out with a faster one later. I think I got that right. Hopefully I won't lose too much Hacker News karma. So this is sort of the thing that I'm saying is like, build your app in a different thing and then replace chunks of it in Rust where it's appropriate. And so here, that's actually the end slide. I want to show you, I've actually done this. I have a little sample application that is totally trivial, but shows off how to do this. So these slides are also in this repository, but also all this source code. So if you go to my GitHub, Steve Klabnik forward 2015, the slides I was just showing you are actually generated by the Rust documentation tool itself. So we actually wrote a little bit of JavaScript that you can include, so it makes slideshows, which is really neat, because like if I had a bunch of Rust code in the slides, I could actually like have the Rust compiler type check my slides, which is neat. So all that crap is in there, but the real big thing are these three directories: Node, rsgex, rizgex. I named it terribly because I knew I was going to be speaking it on stage, and so I made it as hard to pronounce as possible. And then this Rust directory. So the way that this sort of works is inside the Node directory. Let's see, is this the first one? Yeah. So inside the Node directory, I have this little application that doesn't do anything of worth, but it will show you the basic idea. So in it, I require this regular expression library for Node. You can use the JavaScript native regular expressions, but I wanted to use another like extension. I actually will show you a pull request in a minute that compares all three of them. But then chai is just basically this assert library. And so the documentation for the regex package has this example of just this regular expression that is A or B, asterisk ABB. I did Perl before I did Ruby, so I like love regular expressions, but I know a lot of people really hate them. So this is just the example that I went with because I love them, so sorry if you're not into regular expressions. But this just checks a bunch of very simple small strings and sees if it's true or false. I realize that assert equal to true is like kind of bad form, but I like the matching with like assert false, and I don't know, whatever. I just did it this way. And so then I print done. And then I have this other thing that requires, in Rust, we use .rs as our file extension, which is also fun because it's the national TLD of Serbia. So I have like Brooklyn RS for this Rust meetup that I theoretically run in New York that I've done twice in the last year. And so I have Brooklyn.rs, and I had to like give my credit card to this like Serbian DNS registrar, so that's fun. So I decided regex starts with an R as well, so I would name the library rsgex after the Rust extension. Like I said, I now have to say it on stage, so that's what happens sometimes. You name things in a way that you can't pronounce when you know you're going to have to pronounce them. So anyway, the same thing. Rust's regular expression library has slightly different syntax. You can see there's like forward slashes because you can actually do a regular expression literal in JavaScript. We don't have regular expression literals in Rust. So we have the caret and the $sign for the end anchors, which is more of like a Perl regular expression thing. We run the exact same tests and then print done. So I actually have I have the code here. Let's see, forward. Can't cite. All right, this needs to be bigger. Yeah. Let's get rid of that real quick. Okay, much better. So I have a make file that then actually compiles all the stuff. So first it compiles my slides, and then it goes into the Rust directory and it builds the Rust library, and then it goes into the Node directory and runs that script I just showed you, and you can see done. So we successfully executed both sets of regular expressions, and all of those unit tests passed. Everything worked out just peachy. So that's my sort of live example of this running. You can run it yourself, but I want to actually show you now the code. So in your application, you can see how requiring, I use this local thing because NPM's file requirement thing was causing me problems, so I just decided to use a relative path. You would probably publish this as a package, so you would not use the relative path, you just say require rsgex, but the point is that this, from the user of your library, this looks exactly like JavaScript, and it works just like JavaScript. But inside, it's all actually Rust code. So let's take a look at that. This is the rsgex index.js library. And so basically here, I'm using the Node FFI module and the ref module to make this FFI wrapper. I have a fun story about that I'll share at the end. But basically, what happens is I define, okay, I need an rsgex type, and I need a pointer to rsgex. And then this line 7 loads up the library. So inside the Rust directory, I eventually make a .so, which is a shared object. Or if you're on a Mac, it's a dilib. Since I'm on Linux, I just hard-coded it because it's a presentation. And it's not like for general consumption. But the point is that shared object is just like a C shared object. So the example for FFI does this with a C library, but you can do this with just Rust. And so there's two functions, new and match. And these are sort of the return types that you would expect. So you sort of make those out of JavaScript types and then these two other types that I defined. And then in the exports for this module, I say that I'm going to export two functions. One is new, which is just calling into the libraries rsnew, and match, which calls into the libraries rsmatch, and then we're good. Fun multi-language interop story. I had to call this rsmatch because match is a keyword in Rust, and so I couldn't actually name the function match. And so I was just like, oh, whatever, I'll just prefix it with rs for Rust. But I originally just wanted to call it new and match. And so I do that sort of mapping when I do the exports. So this is all you need if you have the library written up. You write this little tiny bit of JavaScript, and then it knows how to load all this stuff from what it thinks is a C library, but it's actually a Rust library. And then in here, this is some Rust code, which frankly, so the FFI stuff is like it's as intense as Rust gets, I'll say, because you have to shuffle from like the C types to the Rust types. So so this is sort of what this looks like. So we make an actual structure, and then here's the implementation of rsnew, which basically these first 3 lines are just converting a C string into a Rust string. So Rust strings are UTF-8 enabled by default. C strings are like whatever crap you put in there. So there's a bunch of like these lines to basically turn the C string stuff into the Rust string stuff. I literally like copied and pasted this from some documentation that I wrote, so it's relatively boilerplate. And I'm working on some libraries to write the boilerplate for you, so you don't even need to think about that. But we basically like load up a regular expression, and then because this is a demo, I'm just like leaking memory everywhere. So I have like an allocate but not a delete function. So every time you make a new regular expression, it just allocates more and more memory. So demos, it's slides, woohoo. But you might implement more. And then this match function does literally the same lines of code, which I probably should have extracted to a function, but nobody's perfect. And I just call out to the Rust regular expression library is match. Last thing I want to show you really briefly, and I don't expect you to understand this code instantly. I guess the point is I'm just telling you it's like relatively easy, or it's like a small number of lines of code to do this kind of thing. Rust actually supports unit testing in the language itself. So I made this little submodule with a test and then checked out that if I had a particular regular expression and some text, it would match against it. So I was actually like checking the validity in the Rust code itself. So anyway, nobody understands piles of code on slides, so I'm not going to explain more than that. You can check out the details, and/or I'd be happy to explain it to you when I'm not on a stage about specifically how that all works. And so yeah, so this is just like delegating. So we now have basically this is now Node calling out to the FFI library, calling out to what it thinks is a C library, which is actually a Rust library, which is calling into the Rust regular expression library, and then performing the match, and then like moving that the whole way back up the chain. So what's fun about this is I was like, yeah, because like Rust has really fast regular expressions. And so my partner, Ashley, is used to calling me on my crap, as partners often do. Oh no, the internet's down. So okay, so I can't actually show you this. On this repository, if you click on this pull requests button, there's a pull request with a benchmark that actually demonstrates that the Rust ends up being way slower than just using a freaking JavaScript regular expression in the first place. And so this is my message to you about performance, is you need to actually, if you're doing this kind of stuff, you need to actually be doing a significant amount of work in the Rust side, because basically all of that translation from JavaScript to C to Rust takes up so much time that you lose all the speed benefits of just matching like a 5-character string against a 3-character string in the first place, right? Like JavaScript is plenty fast at doing that. So I don't want to tell you that you can just like instantly rewrite all your code in Rust and it's automatically faster. Like any sort of claims about speed, you have to actually benchmark things and test them to make sure that they're actually faster. You can't just think about it because compilers are magic and they do all sorts of stuff you don't think about. And so JavaScript is actually plenty fast in most cases. So if I was doing a substantial amount of work here, I think I would fare much better. But yeah, that's just what I want to tell you. Is like the point is it's not always inherently faster. And also, as I mentioned before, I'm actually running out of time, so I'll just say this really briefly. I'm actually working on some libraries specifically for Node and also then for Ruby and Python that will actually eliminate the need for the FFI library in that chain of things. So I can actually take the V8 internal object that Node is using and then just access it directly in the Rust. And so I expect that library to make this kind of process even faster than it is right now, because the FFI library is very convenient, but it also has a lot of overhead. So look out for that in the future. But I guess what I'm saying is making languages play with each other is super fun. I plan on doing it to help you be able to do it in the future. And thank you very much for having me.